Right now, a storm larger than Earth has been raging for over 150 years. Its winds reach 400 miles per hour, but that storm is not the reason Jupiter is the most violent planet in the solar system. Beneath the clouds, pressure crushes hydrogen into liquid metal. Above them, radiation belts accelerate particles to nearly the speed of light, creating a kill zone that fries spacecraft electronics in hours. Jupiter's magnetic field stretches 20 million kilometers across, dwarfing the Sun itself. Its gravity rips moons apart from the inside, flings comets across the solar system, and prevents an entire planet from ever forming. This is not a gentle giant. This is a planetary engine of destruction, operating on every physical scale at once. If you want to understand why nothing in the solar system compares to Jupiter's violence, hit that like button and subscribe. Now, settle in and get yourself comfortable. Let's begin. Imagine falling into Jupiter. You would not hit the ground because there is no ground. There is no surface, no bedrock, no ocean floor, no continent, nothing solid beneath you at all. You would simply fall through thickening layers of gas that grow hotter and denser with every passing second. The sky above would close like a fist. Clouds of ammonia ice would give way to deeper layers of ammonium hydrosulfide, then to water vapor and water ice. The temperature would climb. The pressure would build. Within a few hundred kilometers, the hydrogen atmosphere surrounding you would compress into a liquid, and you would not be falling through air anymore. You would be sinking through a boiling ocean with no surface and no bottom. Deeper still, the pressure would crush that liquid hydrogen into something even stranger, a metallic fluid that conducts electricity and generates the most powerful planetary magnetic field in the solar system. You would never land. You would simply be absorbed, compressed, and erased. That is what Jupiter's atmosphere does to everything that enters it. And it is not a passive process. The atmosphere is not sitting quietly, waiting for visitors. It is a planet-sized engine of convective fury, driven from below by heat that has been building since the formation of the solar system itself. Jupiter is not a world with weather on top of it. Jupiter is weather. From its frozen cloud tops to the crushing depths where hydrogen becomes metal, the entire planet is an atmospheric machine operating without a pause, without a flaw, and without mercy. Most people know Jupiter has storms. They picture the Great Red Spot, a swirling oval of rusty clouds, and assume that is the story. A big storm on a big planet. Impressive, sure, but not fundamentally different from a hurricane on Earth scaled up to match a larger world. That assumption is completely wrong. The Great Red Spot is not Jupiter's violence. It is a symptom of it. One blemish on a face covered in scars that stretch from pole to pole. Jupiter does not have a storm. Jupiter is a storm. The entire visible surface of the planet is weather in motion. Every band, every swirl, every white oval and brown barge and turbulent eddy you see in photographs represents atmospheric violence, operating on scales that make terrestrial weather look like a ripple in a bathtub. The banded structure itself, those alternating light zones and dark belts wrapping horizontally around the planet, are not decorative. They are not static. They are opposing rivers of gas, counter-rotating jet streams screaming past each other at hundreds of miles per hour. The light-coloured zones represent upwelling regions where gas rises from deeper layers and cools, forming high-altitude clouds of ammonia ice that reflect sunlight. The darker belts represent regions where the atmosphere sinks downward, revealing warmer, deeper layers beneath. These bands are not painted on. They are the visible expression of a global circulation pattern driven by Jupiter's rapid rotation and its immense internal heat, and they move. Where the jet streams marking band boundaries meet, the shear between them generates enormous vortices, cyclones and anticyclones grinding into existence where rivers of gas collide at differential speeds that dwarf anything a terrestrial atmosphere can produce. Some of these vortices are the size of entire continents. Some last for days. Others persist for decades or centuries. The atmosphere manufactures them constantly, an endless production line of spinning storms fed by the energy of opposing flows. The Great Red Spot sits trapped between two of these jet streams, locked in place like a ball bearing caught between two conveyor belts running in opposite directions. It is an anticyclone, a region of high atmospheric pressure that rotates counterclockwise in Jupiter's southern hemisphere. Winds at its edges reach approximately 400 miles per hour. The storm is wider than Earth. Its cloud tops tower roughly 8 kilometers above the surrounding cloud deck. It has been observed continuously for at least 150 years, and possibly much longer, since astronomers in the 1600s reported seeing a large spot on Jupiter's face through the earliest telescopes. No storm on Earth lasts more than a few weeks. The most powerful hurricanes our planet has ever generated exhaust themselves in days. This one has persisted for centuries, fed by energy sources that never deplete, maintained by atmospheric dynamics that have no terrestrial parallel. And here is what makes it more unsettling than its longevity alone. Recent observations from the Hubble Space Telescope, collected over 90 days between December 2023 and March 2024, revealed that the Great Red Spot is not stable. It is oscillating. The entire structure jiggles like a bowl of gelatin, changing its size and shape on timescales that surprised even the scientists who have studied it for years. Its dimensions pulse in and out. Its internal rotation fluctuates. The storm is alive in a way researchers did not expect, behaving less like a fixed atmospheric feature and more like something breathing. But the Great Red Spot is also shrinking. Observations spanning recent decades show it has been losing width steadily, and the rate of that shrinkage has drawn significant scientific attention. Research published in 2026 in the journal Icarus proposed an explanation that connects Jupiter's storm to a process familiar to meteorologists on Earth. A team led by Caleb Keaveney at Yale University suggested that fewer surrounding storms are being consumed by the red spot, depriving it of the rotational energy and mass it needs to maintain its size. On Earth, persistent high-pressure systems like heat domes grow and sustain themselves partly by absorbing smaller weather systems that wander into their influence. Jupiter's great anticyclone appears to work on the same principle. Feed it fewer storms, and it starves. Its diameter has already shrunk dramatically from historical measurements. Whether the Great Red Spot will eventually vanish entirely remains an open question that only continued observation can resolve. But its decline does not mean Jupiter is becoming calmer. The opposite may be closer to the truth. Hubble's annual portraits of Jupiter under the Outer Planet Atmosphere's Legacy program consistently show a planet crawling with atmospheric activity. White ovals drift through the southern hemisphere. Brown barges darken the northern belts. Smaller red spots have appeared and merged with existing features. Unnamed cyclones form, intensify, and dissipate in cycles that play out over months and years. Even if the Great Red Spot eventually fades, Jupiter will not become peaceful. The atmospheric engine producing storms will simply redirect its energy into other features. The planet has been generating vortices for billions of years. Losing one, even the most famous one, changes nothing about the machine that created it. What drives all of this fury is not the Sun. That is a critical distinction between Jupiter and Earth, and it is the key to understanding why Jupiter's atmosphere is so relentlessly violent. On our planet, weather is powered primarily by solar heating. The Sun warms the equator more than the poles, creates temperature gradients between land and ocean, and drives the atmospheric circulation patterns that produce wind, rain, and storms. Remove the Sun from the equation, and Earth's weather dies. Jupiter receives roughly 27 times less solar energy per square meter than Earth does, because it orbits more than 5 times farther from the Sun. If solar energy were the dominant driver, Jupiter should be a quiet, frigid world with sluggish winds and minimal convection, a cold ball of gas drifting through the outer solar system with an atmosphere barely stirring. Instead, it is one of the most turbulent atmospheres ever observed by any instrument humans have built. The reason is internal heat. Jupiter radiates approximately 1.7 times more energy than it receives from the Sun. That extra energy comes from deep inside the planet, a remnant of gravitational contraction that has been ongoing since Jupiter formed 4.5 billion years ago. The planet is still slowly shrinking, compressing under its own immense mass, and as it compresses, gravitational potential energy converts into thermal energy. This heat rises through the atmosphere in powerful convective currents that churn the cloud layers from below. Jupiter's weather is not painted on from the outside by distant sunlight. It is pushed upward from the inside by a furnace that ignited when the solar system was young and has never gone cold. The atmosphere is not reacting to its environment. It is expressing its own internal energy, and that energy is enormous. This internal engine produces meteorological phenomena that have no analogue on our planet. Consider lightning. On Earth, lightning forms when water droplets and ice crystals collide inside thunderstorm clouds, building up static charge until the electrical potential discharges in a brilliant bolt. Jupiter has lightning too, but it is radically different in both mechanism and power. NASA's Juno spacecraft, which entered orbit around Jupiter on July 4, 2016, and continued studying the planet through at least 2026, detected two distinct types of Jovian lightning. The first type originates deep in the atmosphere, in water clouds where temperatures and pressures are high enough for liquid water to exist. This deep lightning was first detected by the Voyager missions in 1979, but Juno discovered something no one anticipated. A second type of lightning, called shallow lightning, forms high in the atmosphere where temperatures are far too cold for liquid water to exist. Up there, only ice crystals should survive. No liquid, no charge separation, no mechanism for generating lightning, and yet Juno recorded it, flash after flash erupting from cloud tops that should have been electrically dead. The explanation turned out to be stranger than the mystery itself. Jupiter's upper atmosphere contains abundant ammonia gas. When powerful updrafts launch water ice crystals into these frigid upper layers, ammonia binds to the ice and acts as a chemical antifreeze, melting it into an ammonia-water liquid, even at temperatures that should freeze everything solid. When these ammonia water droplets collide with ice crystals still being hurled upward by convective storms, they generate electrical charge through exactly the same friction process that creates lightning on Earth. And so lightning erupts in a region of the atmosphere that has no business producing it. During 12 flybys, Juno recorded 613 microwave pulses from Jovian lightning. The energy of individual flashes ranged from roughly comparable to a terrestrial lightning bolt up to at least 100 times stronger. But because of uncertainties in cross-planet comparisons, some of Jupiter's flashes could potentially have been up to 1,000,000 times more powerful than anything produced on Earth. A single bolt of Jovian lightning might release more energy than an entire terrestrial thunderstorm generates across its full lifetime. But the shallow lightning discovery cracked open an even deeper puzzle. Juno's microwave radiometer instrument revealed that ammonia is not evenly distributed in Jupiter's upper atmosphere. Large regions showed dramatic ammonia depletion, vast pockets where the gas had been stripped away to depths of roughly 150 kilometers. This was baffling. Jupiter's atmosphere appears violently turbulent when observed from the outside, which should keep all its chemical components thoroughly mixed. Ammonia should be distributed roughly uniformly at every altitude and every latitude. It was not. Something was selectively removing ammonia from enormous stretches of the upper atmosphere and transporting it downward into the planet's depths. As Scott Bolton, Juno's principal investigator, noted, the team had not previously realized how deep these pockets of missing ammonia extended, or how much of Jupiter they covered. The answer, developed by Juno's science team and refined over years of painstaking analysis, turned out to be one of the most exotic weather phenomena ever identified on any world. The ammonia water liquid created during shallow lightning events does not simply remain in the cloud tops. It coats ice crystals to form slushy hailstones that the science team named mushballs. These mushballs are not small, delicate particles. They can grow to substantial size, heavy enough that even Jupiter's powerful updrafts cannot keep them suspended. They plunge downward through the atmosphere, falling through layers of increasing temperature and pressure, carrying their payload of ammonia and water deep into the planet's interior. As they descend into warmer regions, the mushballs melt and evaporate, releasing their chemical cargo far below the visible cloud deck. This process essentially kidnaps ammonia from the upper atmosphere and dumps it into the abyss, creating the depletion zones that Juno detected. Research published in April 2025 in the journal Science Advances provided the strongest confirmation yet that mushballs are real and that they dominate Jupiter's ammonia transport. Chris Mokel, a researcher at the University of California at Berkeley's Space Sciences Laboratory, had initially set out to disprove the mushball theory, because it seemed far too elaborate and too dependent on specific atmospheric conditions to actually work. He spent 3 years trying to demonstrate that the theory was wrong. The data won every time. The mushballs are real. They operate on a planetary scale, and they reshape the chemical structure of Jupiter's atmosphere through a recycling process that has likely been running for billions of years. This is weather unlike anything that exists on Earth. Hailstones made of ammonia slush, plunging through an atmosphere with no floor, transporting chemicals between invisible layers in a cycle driven by forces we only recently learned to measure. Juno also revealed that Jupiter's weather layer is far deeper than anyone expected before the mission launched. Earlier models assumed that the visible cloud bands and jet streams were relatively shallow features, perhaps a few tens of kilometers deep, sitting like decorations on the surface of a much calmer, deeper interior. Juno's precision gravity measurements destroyed that assumption. The jet streams penetrate approximately 3,000 kilometers below the cloud tops. That depth is comparable to the radius of Mars. The weather you see in photographs of Jupiter is not a thin shell. It occupies a significant fraction of the planet's outer volume, a churning layer of atmospheric circulation that extends deeper than some entire planets are wide. Below that weather layer, the atmosphere transitions into a region where hydrogen is compressed into a liquid. The boundary is not sharp. There is no ocean surface to cross. The gas simply becomes denser and denser until it behaves like a fluid, and the fluid becomes denser and denser until it behaves like a metal. This transition happens gradually over thousands of kilometers, a slow dissolution of one state of matter into another with no seam, no edge, and no landmark. The pressure at the depth where hydrogen becomes metallic is approximately 2 million atmospheres. The temperature exceeds 10,000 degrees. At the very center of Jupiter lies a core that remains one of the least understood regions of any planet in the solar system. Juno's gravity data suggest it is not a neat, solid ball of rock and ice as older models predicted. Instead, it appears to be a diffuse, dilute mixture of heavy elements blended into the surrounding metallic hydrogen. The core may be dissolving into the planet around it, or it may never have been fully consolidated in the first place. Either way, the interior of Jupiter is not a place in any sense that humans understand the word. It is a gradient, a continuous transition from thin gas to crushing metallic fluid, with no boundaries, no surfaces, no solid ground, and no refuge at any depth. What this means for anything entering Jupiter's atmosphere is total destruction. No spacecraft ever built could survive a descent into the deep atmosphere. The Galileo atmospheric probe, which NASA deliberately sent plunging into Jupiter in December of 1995, transmitted data for approximately 57 minutes before all contact was lost. During that brief window, it descended roughly 150 kilometers into the atmosphere, encountering temperatures exceeding 300 degrees Fahrenheit and pressures of approximately 22 times Earth's sea level atmosphere. That descent barely scratched the outermost fraction of Jupiter's atmospheric depth. The probe was eventually crushed, melted, and vaporized, its atoms absorbed into Jupiter's atmosphere as if it had never existed. The planet consumed it completely and without effort, and Jupiter does this to everything that enters it, not just spacecraft. Comets, asteroids, meteoroids, any solid object that crosses into Jupiter's gravity well and descends into the atmosphere meets the same fate. The incoming object encounters rapidly thickening gas that decelerates it with tremendous force, converting kinetic energy into heat. The temperatures generated during atmospheric entry can briefly exceed the surface temperature of the Sun. The object does not crash into anything. There is nothing to crash into. It simply burns, fragments, and dissolves into the endless atmosphere. Jupiter eats what it catches, and the atmosphere leaves no wreckage, no crater, no memorial. Just absorption, just erasure. The James Webb Space Telescope added yet another dimension to this picture in 2023, when it discovered a previously unknown jet stream in Jupiter's upper atmosphere. This feature, located above the main cloud deck at altitudes where hazes and aerosols form, spans more than 4,800 kilometers in width and moves at approximately 320 miles per hour. It sits above the deeper weather layer that Juno studies, meaning Jupiter has atmospheric dynamics operating on multiple vertical levels simultaneously. The planet's atmosphere is not one weather system. It is a stack of interlocking systems, each operating at a different altitude, driven by different combinations of internal heat and solar energy, interacting with each other in ways scientists are still working to untangle. Every new instrument that observes Jupiter discovers features that previous instruments missed. The atmosphere has more complexity than any single mission can fully map. Consider what all of this adds up to: a planet with no surface, an atmosphere that extends from thin, frozen cloud tops down to a core of metallic fluid at millions of atmospheres of pressure. Thousands of simultaneous storms, some lasting centuries, grinding against each other along counter-rotating jet streams. Lightning that may be 1,000,000 times more powerful than any bolt that has ever struck the Earth. Exotic hailstones made of ammonia slush, cycling chemicals between invisible atmospheric layers in a process that operates on a planetary scale. A weather engine driven not by the distant sun but by an internal furnace that has burned continuously for 4.5 billion years. An atmospheric circulation so deep it extends to a depth comparable to the diameter of a small planet, and a demonstrated ability to consume everything that enters the atmosphere, from robotic space probes to comets, without leaving a single trace behind. This is Jupiter's first layer of violence, the part you can see in photographs, the swirling bands and colourful vortices that make the planet look almost artistic from a safe distance. But beauty observed from far away becomes brutality experienced up close. Every one of those elegant cloud features represents atmospheric forces that would shred any structure humans have ever built or could conceivably build. The Great Red Spot alone contains winds that exceed the strongest Category 5 hurricane on Earth by a factor of 2, and the red spot is merely one storm among thousands, a single feature operating inside a weather machine, with no off switch, no ceiling, and no bottom. Yet here is what most people never learn, and what transforms Jupiter from merely impressive to genuinely terrifying. The atmosphere, as violent as it is, represents only the most visible dimension of Jupiter's hostility. It is the part we can photograph, the part that fills documentaries and textbook illustrations. But the planet's most lethal danger does not live in the clouds. It lives above them, in a vast invisible structure that turns the space surrounding Jupiter into the most dangerous radiation environment in the entire solar system. The atmosphere can crush you and dissolve you. What surrounds the planet can kill you long before you ever get close enough to touch a cloud. And that is where this story goes next. If you could strip away Jupiter's clouds and see the space surrounding the planet in a wavelength the human eye cannot detect, you would not see emptiness. You would see a structure. A vast, invisible architecture of magnetic force and trapped radiation extending outward from the planet in every direction, stretching so far that it dwarfs the physical body of Jupiter, the way a city dwarfs the building at its center. This structure has a name. It is called the magnetosphere. And it is not a minor feature. It is the single largest persistent structure in the entire solar system, larger than the Sun itself, larger than any storm or cloud band or atmospheric phenomenon Jupiter produces. If you could somehow see it with your bare eyes, it would dominate the sky from the surface of any world within hundreds of millions of kilometers. Jupiter's magnetosphere spans, on average, approximately 20 million kilometers from one side to the other. That is roughly 150 times the diameter of the planet itself, and nearly 15 times the diameter of the Sun. Its exact size fluctuates. The solar wind, a stream of charged particles radiating outward from the Sun at speeds of several hundred kilometers per second, pushes against the magnetosphere on the side facing the Sun, compressing it slightly. On the opposite side, the magnetosphere stretches downstream in an elongated tail that reaches beyond the orbit of Saturn, extending at least 750 million kilometers into deep space. If the magnetosphere were visible, you could stand on Earth and watch it change shape as the solar wind gusted and subsided, an invisible balloon the size of a small solar system breathing in and out, with the rhythm of stellar weather originating 93 million miles away. Nothing else in the solar system comes close to this scale. Earth has a magnetosphere too. It protects our planet from solar radiation and makes life on the surface possible. But Earth's total magnetic dipole moment, the overall strength of its magnetic field as a whole, is roughly 20,000 times weaker than Jupiter's, and its magnetosphere is proportionally tiny. Saturn, Uranus, and Neptune each generate their own magnetic fields, but none approach the intensity or extent of Jupiter's magnetic dominion. The gas giant's magnetosphere is in a category by itself. It is not simply bigger than the others. It is qualitatively different, operating at energy levels and spatial scales that place it closer to astrophysical phenomena than to anything else produced by a planet. The engine that generates this structure lies deep beneath Jupiter's cloud tops, in the region where the atmosphere ceases to be gas and becomes something that exists nowhere on Earth's surface. At depths of approximately 20,000 kilometers below the visible clouds, the pressure and temperature reach levels where hydrogen undergoes a transformation that still challenges physicists to model accurately. Under millions of atmospheres of pressure, hydrogen molecules are forced so close together that their electrons break free from individual atoms and flow collectively. Like electrons in a wire, the hydrogen becomes metallic, it conducts electricity, and it moves. Jupiter's rotation, the fastest of any planet in the solar system, causes this metallic hydrogen ocean to circulate in enormous convective currents. Moving conductive fluid generates a magnetic field. This is the dynamo process, the same fundamental mechanism that creates Earth's magnetic field through the motion of liquid iron in our planet's outer core. But Jupiter's dynamo operates on a scale that is incomparably larger. The metallic hydrogen layer extends over tens of thousands of kilometers. The rotational speed is ferocious. The resulting magnetic field is monstrous. At Jupiter's cloud tops, the local magnetic field intensity measures approximately 4 Gauss at the equator, rising to over 10 Gauss near the poles. Even the equatorial value is roughly 10 times the field strength measured at Earth's surface, and this local intensity only hints at the total magnetic power of the system. That alone would be notable but not extraordinary. The extraordinary part is the volume of space that field controls. Because the field is so strong and the planet rotates so fast, the magnetosphere inflates to a volume that could contain roughly 1,000 suns. It dominates a region of space so vast that charged particles entering it are not just deflected, as they are by Earth's magnetic field. They are captured, trapped in looping orbits along magnetic field lines, and accelerated to speeds that approach the fundamental speed limit of the universe. This is where Jupiter's invisible violence begins. The radiation belts encircling Jupiter are the most hazardous in the solar system. They are not a scaled-up version of Earth's Van Allen belts. They are a fundamentally different kind of radiation environment, operating at energies that make Earth's trapped particle populations look tame. Jupiter's radiation belts contain protons accelerated to approximately 100 billion electron volts. They contain electrons at approximately 100 million electron volts. They contain heavy ions, oxygen and sulfur stripped of their electrons by the violent electromagnetic environment, racing along magnetic field lines at velocities approaching the speed of light. These are not theoretical numbers. They are measured values confirmed by multiple spacecraft, instruments that, in several cases, were damaged or degraded by the very particles they were measuring. The energies involved place Jupiter's radiation belts in the same category as human-built particle accelerators. The protons trapped in Jupiter's magnetosphere carry energies comparable to those produced by the largest colliders on Earth. But Jupiter does not need a tunnel lined with superconducting magnets. It does not need a power grid feeding billions of watts into a controlled beam. The planet accomplishes the same acceleration passively, using nothing but its rotating magnetic field and the endless supply of charged particles that feeds the system from multiple sources. Jupiter is a natural particle accelerator, and it runs continuously, without maintenance, without fuel, and without any mechanism that could shut it down. The primary fuel source for this accelerator is one of Jupiter's own moons. Io, the innermost of the 4 large Galilean satellites, is a world in perpetual geological upheaval, its surface constantly reshaped by eruptions driven by tidal forces that will be explored shortly. Those eruptions blast sulfur dioxide and other volcanic gases into space at velocities high enough to escape Io's weak gravity. Once free of the moon, this volcanic material enters Jupiter's magnetosphere, where it is immediately ionized by the intense radiation environment. The atoms lose their electrons. They become charged particles, and charged particles in a magnetic field are trapped. The result is a donut-shaped ring of plasma encircling Jupiter along Io's orbital path, a structure called the Io plasma torus. This torus is one of the densest plasma environments in the solar system, containing ions of sulfur and oxygen in multiple charge states, all circulating around Jupiter at speeds dictated by the planet's magnetic field rotation. The plasma torus is not merely a passive ring of material drifting in orbit. It is actively fed by Io's continuous volcanic output, replenished at a rate of approximately 1 ton of material per second. 1 ton every second, erupted from a moon's surface, ionized by radiation captured by magnetic fields, and added to a reservoir of charged particles that has been accumulating for as long as Io has been volcanically active, which recent observations suggest has been essentially the entire 4.5 billion year history of the solar system. This plasma does not stay in the torus. It diffuses outward through the magnetosphere, driven by centrifugal forces created by Jupiter's rapid rotation. As the plasma moves outward, it interacts with the magnetic field in ways that generate electric currents, plasma waves, and additional particle acceleration. The magnetosphere becomes a self-reinforcing system. Io produces plasma. The plasma inflates the magnetosphere. The expanded magnetosphere captures more solar wind particles. Those particles are accelerated by the rotating magnetic field. The accelerated particles contribute to the radiation belts. The radiation belts bombard the surfaces and tenuous atmospheres of Jupiter's moons, including Io, in a cycle of electromagnetic violence that feeds itself. The radiation dose rates near Jupiter are difficult to comprehend in human terms. At the orbit of Io, approximately 422,000 kilometers from Jupiter's center, the radiation environment delivers a dose that would be lethal to an unshielded human within minutes. Not hours, not days, minutes. A person standing on the surface of Europa, roughly 671,000 kilometers from Jupiter, would receive a lethal radiation dose in a matter of days, even though Europa is significantly farther from the planet than Io is. The radiation does not arrive as a gentle background haze. It arrives as a bombardment of high-energy particles striking at nearly the speed of light, penetrating tissue, shattering molecular bonds, and destroying cellular machinery at the atomic level. Spacecraft fare no better without extraordinary protection. The Galileo orbiter, which studied Jupiter and its moons from 1995 to 2003, experienced progressive radiation damage throughout its 8-year mission. Its instruments degraded, its imaging capabilities were compromised. The spacecraft had been designed with radiation hardening, but Jupiter's environment exceeded design margins in several cases. By the time the mission ended with a deliberate plunge into Jupiter's atmosphere, the spacecraft had absorbed a cumulative radiation dose hundreds of times greater than what would kill a human being. Humanity's first direct encounter with this radiation environment came in December of 1973, when Pioneer 10 became the first spacecraft ever to fly past Jupiter. The probe passed within approximately 130,000 kilometers of the cloud tops, threading through the inner radiation belts at a distance that engineers at NASA's Ames Research Center believed was survivable based on theoretical predictions of the radiation intensity. Those predictions were badly wrong. The radiation Jupiter actually delivered was, across multiple energy ranges, tens to hundreds of times more intense than the models had estimated. Pioneer 10 absorbed a cumulative dose of roughly 500,000 rads during its flyby, a dose that would kill a human being hundreds of times over. The spacecraft's instruments were overwhelmed. Its imaging photopolarimeter, the primary camera system, produced images that were degraded and corrupted by energetic particles striking the detector. Several instruments experienced anomalous readings or temporary failures as radiation penetrated their electronics. False commands were generated by charged particles flipping bits in the spacecraft's logic circuits. The star sensor that provided attitude reference lost track of its guide star repeatedly as the radiation environment saturated the detector. Pioneer 10 survived, but it survived the way a person survives a car accident, functional but damaged, and carrying scars that would never fully heal. Some instruments never returned to their pre-encounter performance levels. Pioneer 11 followed a year later, in December of 1974, on a trajectory that carried it even closer to Jupiter, passing within approximately 43,000 kilometers of the cloud tops. Engineers had adjusted their expectations based on Pioneer 10's experience, hardening some systems and redesigning the flyby geometry to minimize time in the most intense radiation zones. Pioneer 11 still took a beating. The radiation dose was punishing, though the spacecraft's slightly different trajectory helped limit exposure in the worst regions. The data Pioneer 11 returned confirmed that the inner radiation belts were even more intense at lower altitudes, and that the particle energies extended to ranges that challenged the upper limits of what radiation physicists had considered plausible for a planetary magnetosphere. The Pioneer encounters established a pattern that every subsequent Jupiter mission has confirmed. The radiation environment is always worse than predicted. Every model, every simulation, every theoretical estimate that engineers produce before a mission launches turns out to underestimate what Jupiter actually delivers. The planet does not merely meet expectations, it exceeds them systematically every single time. NASA's Juno spacecraft, which arrived at Jupiter in 2016 and has continued operating through at least May of 2026, was engineered specifically around the radiation threat. Its most sensitive electronics are housed inside a titanium radiation vault, approximately the size of a car trunk. The vault walls are roughly 1 centimeter thick, dense enough to stop the majority of incoming energetic particles before they reach the circuit boards and processors inside. But even titanium cannot stop everything. The most energetic particles in Jupiter's radiation belts, the protons at 100 billion electron volts, penetrate shielding that would stop virtually any particle encountered in Earth's orbital environment. Juno survives not by being impervious, but by being strategic. Its polar orbit carries it over Jupiter's poles, and then dives close to the planet beneath the most intense regions of the radiation belts, spending as little time as possible in the zones of highest particle flux. Each close approach, called a perijove, lasts only a few hours. The spacecraft screams through the danger zone and then retreats to the relative safety of the outer magnetosphere for weeks before the next pass. It is a hit-and-run strategy, designed around the acknowledgement that Jupiter's radiation environment cannot be endured. It can only be survived in brief exposures separated by long recovery periods. Even this careful approach takes a toll. Juno's instruments have accumulated radiation damage over years of operation. The spacecraft was originally designed for a primary mission ending in 2017. It has been extended multiple times because the hardware remained functional, but the radiation clock ticks constantly. Every pass through the inner magnetosphere adds to the cumulative dose. Every orbit brings the spacecraft closer to the point where degradation overcomes engineering margin. The fact that Juno was still returning science data and images as recently as its May to 2026 flyby of the small inner moon Thebe is a testament to both the spacecraft's engineering and the careful management of its radiation exposure, but it also speaks to the severity of the environment. No other planet in the solar system requires this level of protective engineering. No other destination in planetary science demands that a spacecraft be built around a radiation vault and flown on a trajectory designed primarily to minimize time spent near the target. The implications for future exploration are sobering. The European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, launched in April 2023 and is scheduled to arrive in the Jovian system in the early 2030s. Its mission will include extensive study of Ganymede, Europa, and Callisto, all of which orbit within Jupiter's magnetosphere. The spacecraft carries its own radiation shielding, but the challenges of operating in Jupiter's radiation environment shaped every aspect of its design, from orbit selection to instrument placement to mission timeline. The COMPASS mission concept, presented in the recent National Academies of Sciences Decadal Survey for Heliophysics, proposes a dedicated mission specifically to study Jupiter's radiation belts with an unprecedented suite of instruments. The concept acknowledges that Jupiter's radiation environment remains poorly understood despite decades of flyby and orbital data. The belts are too intense, too complex, and too dynamic to be fully characterized by missions designed primarily for other purposes. Understanding them requires a mission built around that single objective, equipped to survive the environment long enough to return comprehensive measurements. The fact that such a mission is considered necessary underscores how extreme Jupiter's radiation belts are. We do not propose dedicated radiation belt missions to Saturn, Uranus, or Neptune. Only Jupiter demands that level of focus, because only Jupiter produces a radiation environment that pushes spacecraft engineering to its absolute limits. Jupiter's magnetosphere also produces auroras, but not the kind you would recognize from Earth. Our planet's northern and southern lights are created when charged particles from the solar wind are funneled along magnetic field lines toward the poles, where they collide with atmospheric gases and produce shimmering curtains of colored light. Jupiter's auroras are driven by a fundamentally different process. While some solar wind contribution exists, the primary energy source for Jupiter's auroras is the planet's own rotation. As Jupiter spins, its magnetic field drags the trapped plasma with it, but the plasma in the outer magnetosphere cannot keep up with the rotation speed. This velocity difference generates enormous electrical currents flowing along magnetic field lines between the magnetosphere and Jupiter's upper atmosphere. Where those currents strike the atmosphere, they deposit energy that produces auroral emissions hundreds of times more powerful than anything Earth generates. Jupiter's auroras are permanent. They do not flicker in and out with solar activity the way Earth's do. They burn continuously, fueled by the planet's own rotational energy rather than by the variable solar wind. They emit not just visible light but powerful ultraviolet radiation and X-rays. In 2021, scientists using data from Juno and the European Space Agency's XMM Newton Observatory solved a 40-year mystery by identifying the mechanism behind Jupiter's X-ray auroral flares. The X-rays are produced when heavy ions, oxygen and sulfur from the Io plasma torus, are accelerated along magnetic field lines and slammed into the polar atmosphere at enormous energies. These are not gentle glows, they are particle beam impacts, concentrated streams of heavy ions striking the atmosphere with enough energy to produce radiation that would be classified as hazardous in any laboratory on Earth. The auroras also reveal the electrical connection between Jupiter and its moons. Io, Europa, and Ganymede each leave a visible footprint in Jupiter's auroral emissions. As each moon moves through Jupiter's magnetic field, it generates its own system of electrical currents flowing between the moon and the planet's atmosphere. Io's auroral footprint is the most prominent, a bright spot in Jupiter's aurora that tracks the moon's orbital position like a searchlight following a moving target. This electrical linkage means that Jupiter is not simply influencing its moons at a distance through gravity alone. It is physically connected to them through electromagnetic circuits that carry millions of amperes of current across hundreds of thousands of kilometers of space. The planet and its moons form an integrated electromagnetic system, bound together by invisible currents that transfer energy, accelerate particles, and reshape the space environment around every body in the system. This electromagnetic architecture has consequences that extend far beyond the auroras themselves. The currents flowing between Jupiter and Io heat the moon's tenuous atmosphere, contributing to the atmospheric sputtering that feeds the plasma torus. The radiation belts bombard Europa's icy surface, breaking water molecules apart into hydrogen and oxygen through a process called radiolysis. This radiation-driven chemistry may produce oxidants on Europa's surface that, if they cycle into the moon's subsurface ocean, could provide chemical energy for potential biological processes. Jupiter's magnetosphere is simultaneously a source of destruction and, possibly, a contributor to habitability. It batters the surfaces of its moons with lethal radiation, while potentially supplying the chemical ingredients that life would need to survive beneath their ice shells. This paradox, violence creating the conditions for something it would also destroy on the surface, captures the strange duality of Jupiter's influence on its own satellite system. The magnetosphere also interacts with the solar wind in ways that create additional violence at its boundaries. The magnetopause, the outer edge of the magnetosphere on the sunward side, is not a smooth, stable surface. It is a dynamic boundary where Jupiter's magnetic field pushes against the pressure of the incoming solar wind. When the solar wind pressure increases, the magnetopause is compressed inward, sometimes by millions of kilometers. When the pressure drops, the magnetosphere expands outward again. These oscillations send shock waves rippling through the magnetosphere, redistributing plasma and energy in ways that can trigger sudden intensifications of the radiation belts. On the downstream side, the magnetotail stretches and occasionally pinches off in events called plasmoid releases, where blobs of plasma are ejected from the magnetotail into interplanetary space. Jupiter does not just trap radiation, it periodically ejects concentrated packets of energized plasma into the solar system, contributing to the broader space weather environment far beyond its own gravitational sphere of influence. What does all of this mean when assembled into a single picture? It means that Jupiter has constructed, through nothing more than the physics of its own composition and rotation, the most lethal radiation environment any planet in the solar system produces. The magnetosphere is not a shield, it is a weapon. It captures particles, accelerates them to relativistic velocities, and concentrates them into belts of radiation so intense that no known biological organism could survive exposure to them. It is powered by the planet's own rotation, fueled by its own moon's volcanic eruptions, and maintained by electromagnetic processes that have been operating without interruption for billions of years. The space surrounding Jupiter is not empty. It is saturated with invisible violence that operates at the atomic level, shredding molecular bonds and destroying electronics with particles moving at nearly the speed of light. And this radiation environment is not the full extent of Jupiter's danger, because the magnetosphere, for all its lethal intensity, is ultimately a consequence of something even more fundamental. The magnetic field is generated by metallic hydrogen set in motion by Jupiter's mass. The radiation belts are fueled by Io's volcanism, which is driven by tidal forces that originate in Jupiter's gravitational field. Every form of invisible violence surrounding the planet traces back to the same root cause, the same force that creates the atmosphere's crushing depth, that powers the weather engine from below, and that inflates the magnetosphere to the size of a small solar system: gravity. Jupiter's gravity is the source of everything, and its gravitational violence reaches far beyond the radiation belts, far beyond the magnetosphere, far beyond the moons, and into the architecture of the solar system itself. That is where this story turns next. Jupiter's mass is not just large, it is dominant. The planet contains approximately 318 times the mass of Earth. That number, by itself, sounds impressive, but abstract. Here is the number that transforms abstract into alarming. Jupiter's mass is 2.5 times the combined mass of every other planet in the solar system added together: Mercury, Venus, Earth, Mars, Saturn, Uranus, Neptune. Stack them all on one side of a cosmic scale. Jupiter, alone, outweighs the pile by a factor of 2.5. In terms of gravitational authority, the solar system does not have 8 planets sharing space. It has the Sun, Jupiter, and everything else. Everything else is secondary. Everything else is subject to Jupiter's influence, whether it orbits nearby or billions of kilometers away. This gravitational supremacy is not passive. Mass warps space. It bends the trajectories of everything that moves through the region it controls. Jupiter does not sit quietly in its orbit, attending to its own atmospheric storms and magnetic fields. It reaches outward. Its gravity extends across the solar system, pulling on asteroids, redirecting comets, perturbing the orbits of other planets, and shaping the distribution of small bodies in ways that have determined the structure of our cosmic neighborhood since the solar system was young. If Jupiter's atmosphere is a weather engine and its magnetosphere is a particle accelerator, then its gravitational field is a hand that rearranges the furniture in every room of the solar system simultaneously, and has been doing so for 4.5 billion years. The most visceral demonstration of Jupiter's gravitational violence does not occur millions of kilometers away in the asteroid belt. It occurs in Jupiter's own backyard, on the tortured surface of its innermost large moon. Io orbits Jupiter at a distance of approximately 422,000 kilometers, completing a full orbit every 42.5 hours. At that proximity, Jupiter's gravitational grip on Io is immense. But gravity alone does not explain what happens to this moon. Gravity, combined with orbital mechanics and the gravitational influence of neighboring moons, produces something far worse than a simple pull. It produces tidal forces so extreme that they have turned Io into the most geologically violent world in the entire solar system. Tidal forces arise because gravity is not uniform across an extended body. The side of Io facing Jupiter is closer to the planet and experiences stronger gravitational attraction than the side facing away. This differential pull stretches Io along the axis pointing toward Jupiter, distorting it from a perfect sphere into a slightly elongated shape. On Earth, The same tidal mechanism raises ocean tides of a meter or two, as the moon's gravity creates a similar, far gentler stretching effect. On Io, the stretching is catastrophic. Jupiter's tidal force on Io is roughly 6,000 times stronger than the moon's tidal force on Earth. That difference does not produce tides 6,000 times larger, because rock does not flow like water, but it produces internal heating on a scale that has no parallel anywhere else in the solar system. The critical factor that amplifies this violence is orbital resonance. Io does not orbit Jupiter in a perfect circle. Its orbit is maintained in a slightly elliptical shape by the gravitational influence of two neighbouring moons, Europa and Ganymede. These three moons are locked in a precise orbital relationship. For every single orbit Ganymede completes, Europa completes exactly 2, and Io completes exactly 4. This resonance means that the three moons periodically align, and each alignment gives Io a small gravitational tug that prevents its orbit from circularizing. A circular orbit would produce constant tidal stretching, uncomfortable but static. An elliptical orbit means the tidal stretching changes continuously as Io moves closer to and farther from Jupiter during each revolution. The planet squeezes and releases the moon in a rhythmic cycle every 42.5 hours. This flexing generates friction inside Io's interior, and friction generates heat, enormous heat. The surface of Io rises and falls by as much as 100 meters during each orbit. 100 meters. That is taller than a 30-story building. Imagine the ground beneath an entire world heaving upward by that distance and then dropping back down again, twice every Earth day, continuously, for billions of years. The energy dissipated by this relentless flexing melts rock inside Io's interior and drives volcanic eruptions across the moon's entire surface. Io has over 400 active volcanoes, more than any other body ever observed. Some of these volcanoes produce lava fountains that shoot hundreds of kilometers above the surface, reaching altitudes so high that the volcanic ejecta escapes Io's gravity entirely and enters Jupiter's magnetosphere. The entire surface of the moon is constantly being repaved by fresh lava flows, meaning Io has virtually no impact craters. Any craters that form are buried within years or decades by new volcanic material. The geological history of the surface is erased as fast as it is written. Recent observations using the Atacama Large Millimeter and Submillimeter Array confirmed in 2024 that Io's extreme volcanism has been ongoing for approximately 4.5 billion years, essentially the entire history of the solar system. This is not a temporary phase. Jupiter has been torturing this moon since it formed. The orbital resonance that maintains Io's elliptical orbit and drives the tidal heating was likely established during the formation of the Galilean moons themselves, meaning the violence was built into the system from the beginning. Io was born into a gravitational arrangement that guaranteed it would be the most volcanically active body in existence, and Jupiter's gravity is the engine that makes it so. The tidal violence does not stop at Io. Europa, the next Galilean moon outward, orbits at approximately 671,000 kilometers from Jupiter. It participates in the same orbital resonance, and while the tidal forces it experiences are weaker than those on Io, they are far from negligible. Europa's tidal heating is sufficient to maintain a global ocean of liquid water beneath the moon's icy crust. This ocean is estimated to contain roughly 2 to 3 times the volume of all Earth's oceans combined, kept liquid not by sunlight, which barely reaches this distance from the Sun, but by the internal heat generated as Jupiter's gravity flexes Europa's interior. The ice shell above that ocean is fractured, ridged, and chaotically disrupted in patterns that speak to constant tidal stress. Europa's surface is one of the youngest in the solar system, geologically speaking, because the ice is continually reworked by forces originating in Jupiter's gravitational field. Ganymede, the largest moon in the solar system, larger even than the planet Mercury, also experiences tidal heating, though at a lower intensity than either Io or Europa. Evidence suggests Ganymede possesses its own subsurface ocean sandwiched between layers of ice, maintained at least partly by the residual tidal energy delivered through the orbital resonance. Even Callisto, the outermost of the 4 Galilean moons and the least geologically active, may harbour a subsurface ocean, though the evidence there is less certain. Jupiter's gravitational influence creates a system where liquid water exists beneath the frozen surfaces of multiple moons simultaneously, sustained entirely by tidal energy rather than solar warmth. The planet has effectively constructed a set of potential habitats for life, buried beneath radiation-blasted ice shells, warmed by gravitational violence rather than by starlight. But Jupiter's gravity does not confine its influence to its own moons. It reaches across the solar system, and one of its most dramatic effects is written in the space between Mars and Jupiter's orbit. The asteroid belt occupies a broad region of the inner solar system, a ring of rocky and metallic debris containing millions of individual objects ranging from dust grains to dwarf planets. Popular imagination pictures the asteroid belt as a dense field of tumbling rocks, a hazardous obstacle course that spacecraft must navigate carefully. The reality is far emptier. The total mass of the entire asteroid belt is less than 4% of the mass of our moon. There is not enough material there to build a respectable planet, and there never will be because Jupiter will not allow it. During the early solar system, roughly 4.5 billion years ago, the region now occupied by the asteroid belt contained far more material, enough potentially to coalesce into a small rocky planet. The process of planetary formation was well underway throughout the inner solar system. Dust grains stuck together to form pebbles. Pebbles accumulated into boulders. Boulders merged into planetesimals kilometers across. These planetesimals should have continued merging into protoplanets and eventually into a fully formed world, the way Mercury, Venus, Earth, and Mars all assembled from similar starting materials in their respective orbital zones. Jupiter prevented it. The gas giant's enormous gravity stirred the orbital velocities of objects in the belt region, pumping energy into their orbits and increasing relative velocities between neighboring bodies. Instead of gentle collisions that allowed objects to stick together and grow, the planetesimals smashed into each other at speeds high enough to shatter them. Accretion reversed. Growth became destruction. Objects that should have been merging were instead fragmenting, chipping, and grinding each other down. Jupiter's gravity created gravitational resonances within the belt, specific orbital periods where the cumulative gravitational tugs from Jupiter add up over many orbits to destabilize any object occupying that zone. These resonances, called Kirkwood gaps after the astronomer who first identified them, are visible today as distinct depletions in the distribution of asteroids at specific distances from the Sun. Objects that wander into a Kirkwood gap are gradually nudged into increasingly eccentric orbits until they are ejected from the belt entirely, either sent inward toward the Sun and the inner planets or flung outward into the cold reaches of the outer solar system. Jupiter did not just fail to protect a planet in this region. It actively and continuously destroyed the possibility of one forming. It stirred the gravitational pot with enough energy to prevent coalescence and then continued stirring for billions of years, maintaining the asteroid belt in its current fragmented state. The belt is not leftover construction material waiting to become a planet. It is a graveyard of planetary potential, maintained in its broken condition by the same gravitational force that assembled Jupiter itself. Every asteroid in the belt represents a piece of a world that was never allowed to exist. This gravitational influence extends further still, reaching outward past the belt and into the realm of comets. Jupiter is the dominant gravitational perturbing body affecting the transfer of comets from the outer solar system into the inner reaches. The vast majority of short-period comets, those with orbital periods of roughly 5 to 6 years, have their aphelia, the most distant points of their orbits, located near Jupiter's orbital distance. These are called Jupiter family comets, and their very existence is a product of Jupiter's gravitational sculpting. These comets originated far beyond Jupiter, in the trans-Neptunian region or the scattered disk at the solar system's edge. Through a series of gravitational encounters with the outer planets, they were gradually handed inward, nudged from orbit to orbit like parcels being passed down a chain. But it is Jupiter that performs the final and most dramatic handoff, capturing these icy bodies into orbits that bring them repeatedly through the inner solar system, where solar heating drives the spectacular tails that make comets visible to observers on Earth. Jupiter's gravitational influence on comets is not a one-way street, and this is where the common narrative gets complicated. For decades, Jupiter has been described as Earth's cosmic shield, a gravitational guardian intercepting dangerous comets and asteroids before they can threaten our planet. There is a kernel of truth in this. Jupiter's gravity well does capture or deflect many objects that might otherwise drift into the inner solar system. But the full picture, based on detailed orbital simulations over the past 2 decades, is considerably more nuanced and less comforting. Jupiter does sometimes deflect comets away from Earth-crossing orbits, but it also sometimes does the opposite. It takes objects that would have remained safely in the outer solar system and redirects them inward, placing them on trajectories that bring them dangerously close to Earth. It creates the short-period comet population that periodically crosses Earth's orbit. It generates gravitational perturbations that can nudge main-belt asteroids out of stable orbits and onto Earth-crossing paths. The planet giveth and the planet taketh away, and the net effect is not a simple shield. It is a complex gravitational filter that both increases and decreases the impact threat to the inner planets, depending on the specific orbital geometry and timing of each encounter. Some researchers have argued that the solar system might actually experience fewer catastrophic impacts if Jupiter did not exist at all, because the gas giant is the primary mechanism by which outer solar system objects are delivered into the inner solar system in the first place. The research supporting this more complicated picture has accumulated steadily over the past 2 decades. In 2008, a team led by Jonathan Horner and Barry Jones published simulations examining how the impact rate on Earth would change if Jupiter were replaced by planets of different masses or removed entirely. Their results challenged the Guardian narrative directly. For asteroid populations, the relationship between Jupiter's mass and Earth's impact risk was not linear. A smaller Jupiter would actually increase the impact rate from certain asteroid populations, because it would perturb their orbits enough to destabilize them, but not enough to eject them from the solar system. A Jupiter-mass planet hit a gravitational sweet spot where its influence was strong enough to both destabilize and remove objects, but the net effect was not a clean shield. It was a filter whose output depended sensitively on the specific population of impactors being considered. For short-period comets, the situation was even more counterintuitive. Jupiter is the primary reason short-period comets exist in the inner solar system at all. Without Jupiter, the gravitational mechanism that transfers comets from the trans-Neptunian region into short-period orbits would largely cease to operate. Earth would face virtually no threat from Jupiter family comets because there would be no Jupiter family comets. The planet creates the very hazard it is popularly credited with preventing. This does not mean Jupiter provides no protection whatsoever. It does deflect and absorb some objects that might otherwise impact Earth, but the net calculation, protection minus threat creation, is not the overwhelming positive that the cosmic shield narrative implies. The honest assessment is that Jupiter is neither purely shield nor purely threat. It is a gravitational agent that both introduces and removes hazards from Earth's vicinity, and the balance between those two effects depends on the type, origin, and orbital characteristics of the objects in question. This complexity mirrors Jupiter's broader relationship with the solar system. The planet does not fit neatly into categories of helpful or harmful. It is both, simultaneously, at every scale. It provided Earth with water and simultaneously bombarded it. It stabilizes some orbits and destabilizes others. It prevents a planet from forming in the asteroid belt, while also preventing the belt from dispersing entirely. Jupiter's gravitational influence is not a service performed on behalf of the inner planets. It is a force that reshapes everything within its reach according to the physics of mass and motion, indifferent to whether the consequences are constructive or destructive for any particular world. The most spectacular demonstration of what happens when Jupiter's gravity captures a comet occurred in July of 1994. Comet Shoemaker-Levy 9 had been orbiting Jupiter, not the Sun, for at least 2 decades before its final encounter. At some point during its captive orbit, the comet passed so close to Jupiter that tidal forces, the same stretching mechanism that tortures Io, tore the comet's nucleus apart into at least 21 major fragments. These fragments, strung out in a line like pearls on a broken necklace, continued orbiting Jupiter on a trajectory that led them directly into the planet's atmosphere. Over 6 days in July of 1994, fragment after fragment plunged into Jupiter's southern hemisphere at velocities of approximately 60 kilometers per second. Each impact released energy measured not in kilotons, but in millions of megatons of TNT equivalent. The largest fragments produced individual explosions that exceeded the total energy output of entire terrestrial volcanic eruptions by orders of magnitude. The impact scars, dark bruises in Jupiter's cloud tops, were visible through amateur telescopes on Earth. The first fragment to strike, designated Fragment A, hit Jupiter's southern hemisphere on July 16, 1994. Telescopes around the world were pointed at the planet, but no one was fully prepared for what they saw. A fireball erupted above Jupiter's limb, rising thousands of kilometers above the cloud tops like a mushroom cloud blooming in slow motion against the blackness of space. The Galileo spacecraft, still nearly a year and a half from its own orbital insertion at Jupiter, but already close enough to observe from a direct line of sight, recorded the flash as it happened. Within minutes, a dark scar appeared in Jupiter's atmosphere at the impact site, a bruise roughly the size of Earth's entire diameter, stamped into the ammonia cloud deck by the energy of a single cometary fragment. And that was only the first one. Over the next 6 days, 20 more fragments followed Fragment A into Jupiter's atmosphere. Each strike produced its own fireball, its own rising plume, its own expanding scar. Fragment G, the largest and most energetic, struck on July 18th and produced an impact that became the single most violent event ever directly observed by human instruments in the solar system. The fireball from Fragment G rose approximately 3,000 kilometers above Jupiter's cloud tops. The temperature of the impact plume briefly exceeded 40,000 degrees, hotter than the surface of the Sun. The dark scar left behind was larger than Earth's diameter, a wound so vast that amateur astronomers with modest backyard telescopes could see it clearly from over 600 million kilometers away. The energy released by Fragment G alone was estimated at over 1 million megatons of TNT equivalent, with some models placing it significantly higher. For context, the most powerful nuclear weapon ever detonated on Earth, the Soviet Tsar bomber, yielded approximately 50 megatons. Even by conservative estimates, Fragment G released the equivalent of more than 20,000 Tsar bombers in a single impact, lasting only a few seconds. The infrared signatures were equally staggering. Instruments at the Keck Observatory and other ground-based facilities recorded thermal emissions from the impact sites that briefly made small regions of Jupiter's atmosphere glow more brightly in infrared wavelengths than the rest of the entire planet combined. The impacts punched holes in the upper atmosphere, exposing deeper, warmer layers that radiated intensely before the cloud decks slowly closed back over them. Spectroscopic analysis of the impact plumes revealed chemicals that had been dredged up from deep inside Jupiter's atmosphere by the explosive energy, compounds like hydrogen sulfide, ammonia, and water that do not normally appear at the altitudes where they were detected. The impacts were effectively drilling into Jupiter, momentarily excavating material from hundreds of kilometers below the visible surface and spraying it into space, giving scientists an unprecedented chemical sample of the deep atmosphere that no spacecraft had been able to reach. Each successive impact added its own scar to a growing chain of dark spots marching across Jupiter's southern hemisphere. Photographs from Hubble showed the planet's face disfigured by a string of bruises, each one a record of violence on a scale that would have been globally catastrophic on Earth. Fragment G alone released an estimated energy of over 1 million megatons, roughly equivalent to 20,000 of the most powerful nuclear weapons ever detonated. For comparison, the Chicxulub asteroid that ended the age of the dinosaurs 66 million years ago released an estimated 100 million megatons, significantly more than any individual Shoemaker-Levy 9 fragment. But the comparison illuminates Jupiter's nature rather than diminishing the impacts. The combined energy of all 21 strikes was roughly 6 million megatons, the most violent directly observed event in recorded astronomical history. Jupiter absorbed it all. The planet consumed an energy release equivalent to 600 times the yield of every nuclear weapon on Earth. And within months, the atmosphere had closed over the scars as if the collisions had never occurred. What would have sterilized a rocky world barely registered as a temporary blemish on this one. Within weeks, Jupiter's atmospheric winds began smearing the dark impact scars into elongated streaks. Within months, the visible marks had largely blended into the surrounding cloud bands, absorbed by the relentless circulation of the atmosphere. Within a year, the scars were effectively gone, Jupiter had consumed a comet that would have been an extinction-level catastrophe on Earth, absorbed the energy of hundreds of thousands of nuclear weapons, and then erased the evidence as casually as a pond smoothing over a handful of thrown stones. Shoemaker-Levy 9 was the first time humans witnessed a planetary-scale impact event in real time. It was observed by the Hubble Space Telescope, the Galileo spacecraft, already en route to Jupiter, and ground-based observatories around the world. The event did not merely demonstrate the power of cometary impacts, it demonstrated what Jupiter does to objects it captures. The comet did not simply fall onto the planet. Jupiter first captured it gravitationally, then tore it apart tidally, then consumed the fragments one by one in a series of explosions that briefly outshone the planet's own thermal emission at infrared wavelengths. The same absorptive capacity that swallowed the Galileo atmospheric probe without leaving a trace had swallowed an entire comet and the energy of hundreds of thousands of nuclear weapons, and the planet showed no lasting consequence whatsoever. Jupiter's appetite is indiscriminate and total. Impact events on Jupiter are not rare. Since Shoemaker-Levy 9, amateur astronomers and professional surveys have detected multiple additional impacts, bright flashes in Jupiter's atmosphere consistent with small asteroid or comet fragments striking the planet. These events occur with a frequency that suggests Jupiter is struck by objects of significant size every few years. The planet's massive cross-section, its enormous gravity well, and its position in the outer solar system make it a natural collector of debris. Some of this debris would otherwise drift through the solar system harmlessly. Some of it might eventually cross Earth's orbit. Jupiter intercepts a fraction of this material, but it also generates new threats by perturbing objects that would otherwise have remained distant and safe. Jupiter's gravitational influence also shaped the orbits of the other planets during the solar system's early history, a period of dynamical upheaval that planetary scientists have studied extensively through computer simulations. Jupiter's gravitational influence also shaped the orbits of the other planets during the solar system's early history, a period of dynamical upheaval that planetary scientists have studied extensively through computer simulations. Leading models propose that Jupiter did not simply form in place and stay there. It migrated, and that migration rewrote the history of every world in the inner solar system. The details of these migration models reveal just how profoundly Jupiter reshaped the solar system's early history. The Grand Tack hypothesis, developed by Kevin Walsh and colleagues, proposes that Jupiter formed at roughly 3.5 astronomical units from the Sun, and then migrated inward to approximately 1.5 astronomical units, nearly as close to the Sun as Mars orbits today. At that distance, Jupiter's gravity would have swept through the region where the terrestrial planets were still forming, scattering planetesimals, truncating the distribution of solid material, and fundamentally altering the amount of mass available to build Mars. This may explain one of the most persistent puzzles in planetary science. Mars is far smaller than Earth, roughly 1/10 its mass, even though simple models of planet formation predict it should be comparable in size. If Jupiter migrated through Mars's formation zone and stripped away much of the available building material before Mars could finish assembling, the red planet's stunted growth becomes a natural consequence of Jupiter's gravitational passage. The Grand Tack does not leave Jupiter in the inner solar system. The model proposes that Saturn, migrating inward as well, eventually caught up and the two planets became locked in a mutual resonance that reversed their migration direction. Jupiter retreated to approximately its current orbital distance of 5.2 astronomical units. But the damage was done. Jupiter's inward sweep had already depleted the inner solar system of material that might otherwise have formed additional planets or made existing ones more massive. The Nice model, named after the French city where it was developed, addresses what happened later. This model proposes that several 100 million years after the planets reached approximately their current positions, a gravitational instability among the giant planets triggered a sudden reorganization of their orbits. Jupiter shifted slightly inward while Saturn, Uranus, and Neptune shifted outward. Neptune's outward migration ploughed through a dense disk of icy planetesimals beyond its original orbit, scattering them in every direction. Some were flung outward to form the Oort cloud, the vast spherical shell of comets surrounding the solar system at distances of thousands to tens of thousands of astronomical units. Others were flung inward, flooding the inner solar system with a surge of cometary and asteroidal debris. This influx of material may have produced the Late Heavy Bombardment, a period of dramatically increased cratering on the Moon, Earth, Mars, and Mercury that left its signature in the ancient surfaces of those worlds. The Moon's heavily cratered highlands preserve the record most clearly, because the Moon lacks the atmospheric and geological processes that erase similar scars on Earth. If the NICE model is correct, the catastrophic bombardment that reshaped the surfaces of every world in the inner solar system 4 billion years ago was a direct consequence of Jupiter's gravitational influence destabilizing the orbits of the outer giant, planets. There is also evidence that Jupiter's migration may have delivered water to Earth. The inner solar system was too hot during its early history for water ice to condense near Earth's orbit. The water that fills our oceans likely arrived later, carried by asteroids and comets from cooler regions beyond the snowline, the distance from the Sun where water ice becomes stable. Jupiter's gravitational interactions with the asteroid belt and with scattered icy bodies may have been the mechanism that sent water-bearing impactors toward the young Earth. If this interpretation is correct, Jupiter simultaneously threatened the inner planets with bombardment and provided them with the water that made life possible. The planet's gravitational violence was, paradoxically, one of the preconditions for our own existence. Whether or not every detail of these migration models proves correct, the underlying principle is confirmed by multiple lines of evidence. Jupiter's gravity has sculpted the solar system. It determined which orbits are stable and which are not. It decided where planets could form and where they could not. It controls the delivery rate of comets into the inner solar system. It maintains the structure of the asteroid belt. It influences the orbital eccentricities of Mars, Earth, and the other terrestrial planets through long-term gravitational perturbations that play out over millions of years. No other planet exerts this kind of systemic influence. Saturn has significant mass, but less than a third of Jupiter's. The ice giants Uranus and Neptune are massive compared to Earth, but minor compared to Jupiter. The terrestrial planets are gravitationally negligible at the scale of the full solar system. Jupiter alone operates as a gravitational architect, and the system we inhabit today is as much a product of Jupiter's influence as it is a product of the Sun's slasher. This architectural control extends to the protection and the endangerment of life on Earth. The same gravitational influence that prevented a planet from forming in the asteroid belt also influences the long-term stability of Earth's orbit. Simulations show that without Jupiter, the eccentricities of the inner planet's orbits would evolve differently over billions of years, potentially leading to orbital instabilities that could eject planets from the solar system or send them crashing into each other. Jupiter's presence constrains these oscillations, acting as a gravitational anchor that keeps the inner solar system's orbital dynamics within certain bounds. But those same simulations show that Jupiter also introduces its own perturbations, subtle but cumulative gravitational nudges that ensure Earth's climate and orbital parameters are never perfectly static. The Milankovitch cycles that drive ice ages on Earth are influenced, indirectly, by the gravitational tugs of Jupiter and Saturn on our planet's orbital elements. Jupiter's gravity reaches from the frozen comet reservoirs beyond Neptune to the inner edge of the asteroid belt and into the orbits of every rocky planet circling the Sun. It rips moons apart from the inside, tears comets into fragments, prevents planets from forming, and sculpts the trajectories of billions of small bodies across the full breadth of the solar system. It acts simultaneously as creator and destroyer, stabilizer and disruptor, shield and threat. No other planet operates on this scale. No other planet combines this kind of gravitational reach with the atmospheric violence and radiation hostility already explored in this story. But each of these forms of violence, the atmospheric fury, the radiation kill zone, and the gravitational domination, has been examined in isolation so far, separated into distinct layers, as if they were independent systems operating side by side. They are not. They are interlocked. Each one feeds the others. Each one depends on Jupiter's mass, Jupiter's rotation, and Jupiter's internal heat. The full picture of Jupiter's violence only emerges when you stop treating these forces as separate chapters and start understanding them as components of a single machine, a machine whose output is hostility at every physical scale, from the molecular to the solar systemic. That machine, and what it means for how we understand this planet, is what the final part of this story will reveal. Everything discussed so far has been treated as if Jupiter's violence comes in separate categories, atmospheric violence in one chapter, radiation violence in another, gravitational violence in a third. 3 distinct threats, 3 independent systems, 3 stories that happen to share the same planet. But that framing is wrong. It is a simplification forced by the limitations of linear storytelling, and it obscures the most important truth about Jupiter. These are not separate systems, they are one system, one interconnected machine where each form of violence generates, sustains, and amplifies the others in a self-reinforcing architecture of planetary hostility that has been operating without interruption for 4.5 billion years. To understand why Jupiter is the most violent planet in the solar system, you cannot simply list its individual dangers. You have to see the connections between them. You have to follow the energy from its origin to its final expression, and recognize that every thread leads back to the same source, and every output feeds back into the same engine. Jupiter is not a planet that happens to have dangerous weather, dangerous radiation, and dangerous gravity. Jupiter is a planet whose mass creates all 3 simultaneously, whose internal physics links them into a single cycle, and whose scale ensures that the cycle operates at intensities no other world in the solar system can approach. Start at the center. Jupiter's core, whatever its precise composition and structure, sits beneath roughly 70,000 kilometers of material, compressed by the planet's own gravitational weight. That gravitational compression is the first link in the chain. Jupiter is still contracting, still slowly shrinking under its own mass, and that contraction converts gravitational potential energy into heat. This is why Jupiter emits nearly twice as much energy as it absorbs from sunlight, a thermal surplus that has persisted since the planet's formation. The planet is its own furnace, burning fuel that is not chemical or nuclear but gravitational. This internal heat rises through the planet's interior in enormous convective currents, churning through the metallic hydrogen layer, pushing upward through the liquid hydrogen region, and finally erupting into the gaseous atmosphere as the convective storms, jet streams, and vortices described earlier. The atmosphere's violence is therefore not an independent phenomenon. It is a direct consequence of mass. Jupiter is massive enough to generate significant internal heat through gravitational contraction alone, and that heat drives weather systems of a ferocity that no externally heated atmosphere could produce. Earth's weather is powered by the sun, a source that delivers energy to the top of the atmosphere and lets convection distribute it downward. Jupiter's weather is powered from below by heat that originates in the gravitational compression of the planet's own bulk. The energy enters the atmosphere from the bottom, pushing upward through thousands of kilometers of thickening gas, generating the deep convective cells that create shallow lightning, mushball precipitation, and jet streams that penetrate 3,000 kilometers below the cloud tops. Remove Jupiter's mass, and the internal heat disappears. Remove the internal heat, and the atmospheric engine stops. The storms are not decorations on a massive planet. They are expressions of its mass, converted through gravitational physics into meteorological fury. Now, follow the energy deeper. The same gravitational compression that heats the atmosphere also creates the conditions for something far more consequential. Deep inside Jupiter, as established earlier, that compression forces hydrogen into a metallic state, a conductive fluid churned into motion by the planet's rotation. That motion generates the magnetic field. The magnetic field inflates the magnetosphere. The magnetosphere traps and accelerates charged particles into the radiation belts. But what matters now is not any single step in this sequence. It is the sequence itself. Each link in the chain depends on the one before it, and every link traces back to the same origin. Mass creates pressure. Pressure creates metallic hydrogen. Metallic hydrogen in motion creates the magnetic field. The magnetic field creates the radiation environment. Remove Jupiter's mass, and every subsequent step collapses. The radiation belts do not exist without the magnetosphere. The magnetosphere does not exist without the dynamo. The dynamo does not exist without metallic hydrogen. The metallic hydrogen does not exist without gravitational compression, sufficient to reach 2 million atmospheres. And that compression does not exist without Jupiter's mass. The entire chain is a single expression of how much matter this planet contains. Jupiter's mass creates the pressure that produces metallic hydrogen. Jupiter's mass drives the contraction that heats the interior and sustains convection in the metallic layer. Jupiter's rotation, maintained by the conservation of angular momentum from the planet's formation, spins the conductive fluid fast enough to generate the dynamo. The magnetosphere, the radiation belts, the relativistic particle environment that makes Jupiter the most hazardous radiation source in the solar system, all of it is a downstream consequence of how much matter Jupiter contains and how fast that matter spins. But the radiation belts are not self-sustaining on magnetic field energy alone. They need fuel. They need a continuous supply of charged particles to replace those that are lost through various processes. Particles that scatter into the atmosphere, escape through the magnetotail, or are absorbed by the surfaces of moons. The primary fuel source is Io. Io's volcanoes continuously inject volcanic gas into space at a rate that replenishes the plasma torus faster than it can drain. That material is ionized by the radiation environment and captured by the magnetic field, feeding the Io plasma torus and ultimately supplying the radiation belts with the heavy ions that make them so lethal. And here is where the loop closes. Why is Io volcanic? Because Jupiter's gravity, acting through tidal forces amplified by orbital resonance with Europa and Ganymede, flexes Io's interior with enough energy to melt rock and drive continuous eruptions across the moon's entire surface. Io's volcanism is a product of Jupiter's mass. The radiation belts are fueled by Io's volcanism. The radiation belts are shaped by the magnetic field. The magnetic field is generated by metallic hydrogen. The metallic hydrogen is created by gravitational compression. Everything connects. Everything feeds back. Gravity produces the conditions for tidal heating. Tidal heating produces volcanic outgassing. Volcanic outgassing feeds the magnetosphere. The magnetosphere concentrates radiation. The radiation bombards the surfaces of the very moons whose gravitational interactions sustain the volcanic source. It is a cycle with no beginning and no end. A closed loop of planetary violence where the output of each process becomes the input for the next. No other planet in the solar system operates this way. Saturn has a magnetic field and radiation belts, but they are far weaker because Saturn's internal dynamo is less powerful and it lacks a volcanic moon feeding its magnetosphere at Io's rate. Saturn has storms, but they are less frequent and less intense because Saturn's internal heat flux is lower. Uranus and Neptune have magnetic fields, but they are tilted and disordered, and their radiation environments are modest by comparison. The terrestrial planets have no significant magnetospheres at all, except for Earth's, which is 20,000 times weaker than Jupiter's. Mars lost its global magnetic field billions of years ago. Venus never developed one. Mercury has a field so weak it barely deflects the solar wind. None of these worlds combine the atmospheric depth, the magnetic intensity, the radiation lethality, and the gravitational reach that Jupiter integrates into a single planetary system. The interlocking nature of Jupiter's violence creates emergent properties that no individual component would produce in isolation. Consider what happens to Europa's surface. Europa orbits within Jupiter's radiation belts, and its icy surface is continuously bombarded by energetic electrons and ions accelerated by the magnetosphere. This bombardment drives radiolysis, the breaking apart of water ice molecules into hydrogen and oxygen through radiation-induced chemistry. The hydrogen, being light, escapes Europa's feeble gravity. The oxygen remains, accumulating on the surface as oxidants, compounds that could serve as chemical energy sources for hypothetical biological processes. If these oxidants cycle downward through fractures in the ice shell and reach the liquid water ocean beneath, they could provide the kind of chemical disequilibrium that life on Earth exploits to survive. But where did the energy come from? The radiation that drives the surface chemistry originates in the magnetosphere, which is powered by the dynamo, which is driven by metallic hydrogen convection, which is sustained by gravitational compression, which is a function of Jupiter's mass. The liquid ocean beneath Europa's ice exists because tidal heating, another consequence of Jupiter's mass acting through gravity, prevents the water from freezing solid. The orbital resonance that maintains the tidal heating involves Io, whose volcanism fuels the very radiation belts that bombard Europa's surface. Every element of this potential habitability scenario, the ocean, the energy source, The chemical ingredients traces back to Jupiter's mass and the interconnected systems it generates. The planet simultaneously creates the conditions under which life might exist and bombards the surface above that life with radiation intense enough to sterilize any organism exposed to it. This is not a contradiction. It is a characteristic of how Jupiter's violence operates. Destruction and creation emerge from the same engine, and neither can be separated from the other. This systemic quality is what elevates Jupiter beyond any simple comparison with other hostile environments in the solar system. Venus has a crushing atmosphere with surface temperatures of approximately 465 degrees Celsius and pressures 90 times Earth's sea level. That is extreme. But it is a single mode of hostility, operating on a single world's surface. Venus does not generate radiation belts. Venus does not tidally destroy moons. Venus does not gravitationally sculpt the orbits of comets and asteroids across the entire solar system. Its violence is local and atmospheric. It stays on Venus. Mars has lethal surface radiation because it lacks a global magnetic field, but that radiation is simply unfiltered solar and cosmic particles striking the surface. Mars does not amplify those particles. It does not accelerate them. It does not produce its own radiation through an internal dynamo feeding trapped particle populations. Mars is passively dangerous. Jupiter is actively dangerous. It manufactures its own radiation from scratch, using energy sources entirely internal to the Jovian system. Even the Sun, the most energetic object in the solar system, produces its violence through a fundamentally different mechanism. The Sun is powered by nuclear fusion, converting hydrogen into helium at temperatures of millions of degrees. Its violence is thermal and radiative, expressed as electromagnetic radiation and the solar wind. But the Sun does not have an atmosphere in the way Jupiter does, with counter-rotating jet streams and thousand-year storms. The Sun does not have a magnetosphere that traps and accelerates particles from an orbiting volcanic moon. The Sun does not tidally shred its own satellites. Jupiter occupies a unique position. It is not massive enough to ignite fusion, falling short by a factor of roughly 75 in mass, but it is massive enough to do nearly everything else. It compresses its own interior to exotic states of matter. It generates magnetic fields of planetary record intensity. It drives weather powered by internal heat. It gravitationally dominates an entire solar system of smaller bodies. It is the closest thing to a star that a planet can be without actually becoming one, and the violence it produces reflects that intermediate status. Too massive to be inert, not massive enough to shine, exactly massive enough to be the most hostile planetary environment within several light-years of Earth, and Jupiter may not even represent the upper limit of what this kind of planetary violence can produce. Over the past 3 decades, astronomers have discovered thousands of exoplanets orbiting other stars, and among the most common and dramatic types are worlds that make Jupiter look moderate by comparison. Hot Jupiters are gas giants with masses comparable to or exceeding Jupiter's, but orbiting their host stars at distances so close that their orbital periods are measured in days rather than years. These worlds receive thousands of times more stellar radiation than Jupiter does. Their atmospheres reach temperatures of 1,000 to 3,000 degrees, hot enough to vaporize rock and iron, creating clouds of silicate droplets and metallic rain. The atmospheric dynamics on such worlds are expected to be extreme beyond anything observed in our solar system, with wind speeds potentially exceeding several thousand miles per hour, driven by the enormous temperature difference between the permanent day side and the permanent night side of tidally locked worlds. If Jupiter's internal heat alone drives atmospheric violence capable of producing 400-mile-per-hour winds and centuries-long storms, imagine what happens when you add the full radiative output of a nearby star blasting one hemisphere continuously. The models suggest atmospheric chaos at energy levels our instruments can barely simulate. Hot Jupiters may be the most violently dynamic atmospheres in the galaxy, and they are fundamentally Jupiter-like objects whose violence has been amplified by an external energy source that our Jupiter does not receive. Super Jupiters push the picture further. These are gas giants with masses 5, 10, or even 15 times Jupiter's, orbiting at various distances from their host stars. Their greater mass means deeper gravitational compression, stronger internal heating, more extreme metallic hydrogen layers, and potentially more powerful magnetic fields. A planet 10 times Jupiter's mass would generate tidal forces on close-orbiting moons that could make Io's volcanism look trivial. Its magnetosphere might extend across a volume that dwarfs even Jupiter's 20 million kilometer structure. Its radiation belts could contain particles at energies that approach the theoretical limits for magnetic trapping. We do not yet have the ability to directly measure the magnetospheres of exoplanets, but the physics is clear. The same mechanisms that make Jupiter violent would operate at amplified intensities on any world that is more massive, rotates faster, or possesses a volcanic moon injecting plasma into its magnetic field at higher rates. What Jupiter teaches us, then, is not merely a lesson about one planet in one solar system. It is a lesson about what mass does. It is a case study in how gravity, magnetism, radiation, and atmospheric physics combine when enough matter accumulates in one place. Jupiter is the solar system's demonstration model for a class of planetary violence that likely occurs throughout the galaxy, on worlds we are only beginning to detect and cannot yet visit. Every hot Jupiter, every super Jupiter, every gas giant orbiting within a few stellar radii of its host star is a variation on the same theme. Mass generates compression. Compression generates heat and exotic matter. Exotic matter in motion generates magnetic fields. Magnetic fields trap and accelerate particles. Gravity tortures moons. Atmospheres devour everything that enters them. The recipe is universal. Our Jupiter, sitting quietly at 5.2 astronomical units from the Sun, bathed in relatively modest sunlight, orbited by a handful of tortured moons, is the mild version of this phenomenon. It is the version we can study from a safe distance with instruments that survive long enough to return data. But it is not the extreme case. It is the local example of a process that, elsewhere in the galaxy, operates at intensities that would make Jupiter's 400 mile-per-hour winds and 100 billion electron-volt protons look gentle. The scale at which Jupiter's violence operates deserves emphasis, because scale is not merely a quantitative detail, it is qualitatively transformative. A storm on Earth might be 100 kilometers across and last a week. A storm on Jupiter can be larger than Earth itself and last for centuries. That is not just a bigger version of the same thing. It is a fundamentally different phenomenon, operating under different physical constraints, sustained by different energy sources, and producing effects that have no terrestrial analogue. Earth's radiation belts contain particles at energies of a few million electron volts. Jupiter's contain particles at 100 billion electron volts. That is not merely more radiation, it is radiation at energies that placed in the domain of high-energy astrophysics, the kind of particle environment associated with supernova remnants and active galactic nuclei, not with planets. Jupiter's gravitational influence extends across the solar system, shaping the orbits of objects billions of kilometers away. Earth's gravity extends barely far enough to hold the Moon. The difference is not just range, it is the difference between a local phenomenon and a systemic one. Jupiter does not merely exist in the solar system. It defines the solar system's structure, determines which orbits are stable, controls the delivery of comets to the inner planets, and prevents planetary formation in an entire region of space. No other planet does this. No other planet can do this. The solar system would be a fundamentally different place without Jupiter, not just missing one planet but restructured at every level from the asteroid belt to the Oort cloud. Understanding Jupiter as a violent system rather than a collection of individual hazards changes how we should think about the planet. It is common in popular science to describe Jupiter with a mixture of awe and admiration. The biggest planet, the most beautiful storms, the most moons. The language frames Jupiter as a superlative, a record holder, a cosmic landmark worth visiting in the imagination, the way one might visit a national park or a famous monument. That framing is dangerously misleading. Jupiter is not a destination. It is an environment of compounding lethality, where every physical process operates at intensities that would destroy any human technology, any biological organism, and any conceivable habitat within minutes to hours of direct exposure. The atmosphere will crush and dissolve you. The radiation will kill you before you reach the atmosphere. The gravity will distort your trajectory, trap your spacecraft, and subject your instruments to forces they were never designed to withstand. And these are not three separate threats you might encounter one at a time. They overlap. They coexist. They reinforce each other in a system that operates without pause and without mercy. There is a tendency in science communication to soften Jupiter with wonder, to focus on the beauty of the cloud bands, the elegance of the orbital resonances, the tantalizing possibility of life beneath Europa's ice. Those things are real. Jupiter is beautiful from a distance. The Voyager and Cassini and Juno images are genuinely stunning, swirling pastels of ammonia and ammonium hydrosulfide, rendered in colors that look almost painterly. The orbital mechanics of the Galilean moons are elegant in their mathematical precision, a clockwork of gravitational ratios that would satisfy any aesthetic sense. And the possibility that Europa's ocean might harbor life is one of the most compelling questions in all of planetary science. But beauty observed from 1 billion kilometers does not negate violence experienced up close. The same cloud bands that look like brushstrokes from Earth orbit are hurricane-force winds grinding against each other at 400 miles per hour. The same orbital resonance that mathematicians admire is the mechanism that tears Io's interior apart and drives volcanic eruptions hot enough to melt silicate rock. The same ocean beneath Europa's ice that might harbor life is maintained by tidal forces that crack, compress, and resurface the ice shell in patterns that record continuous geological stress. Every beautiful feature of the Jovian system is simultaneously a violent one. The aesthetic and the lethal are not separate categories. They are the same physics viewed from different distances. This duality is not unique to Jupiter, but Jupiter expresses it at a scale and intensity unmatched by any other planet. It is the solar system's most magnificent object and its most punishing environment, and those two descriptions refer to the same properties. The mass that creates the beautiful banded atmosphere also creates the crushing pressure that destroys anything entering it. The rotation that drives the elegant magnetic field geometry also powers the radiation belts that sterilize entire moons. The gravity that produces the mathematically precise orbital resonances also rips comets apart and prevents planets from forming. There is no version of Jupiter where the beauty exists without the violence. They are inseparable expressions of the same physical reality. What does it mean then to call Jupiter the most violent planet in the solar system? It means that no other planet combines this many forms of hostility at this intensity across this range of physical scales. It means that Jupiter's violence is not confined to one domain. It is atmospheric, radiative, magnetic, gravitational, and tidal. All simultaneously, all continuously, all originating from the same fundamental source. It means that the violence is not incidental, it is structural. It is built into the planet's mass, rotation, and composition in ways that cannot be separated from what Jupiter fundamentally is. It means that every layer of closer examination reveals not a gentler truth but a deeper form of danger. Zoom in on the clouds, and you find storms that dwarf terrestrial hurricanes by orders of magnitude. Zoom out past the clouds, and you find radiation belts that would kill you in minutes. Zoom out further, and you find a gravitational field that restructures the orbits of objects billions of kilometers away. There is no safe distance from which Jupiter becomes benign. There is only distance at which its violence becomes less immediately lethal. And even at the orbit of Earth, Jupiter's gravitational influence still perturbs our trajectory around the Sun. Jupiter is often called a gas giant, as if the word giant was sufficient to capture what it is. That word is inadequate. A giant is simply something large. Jupiter is not simply large. It is large enough that its size generates physical processes that no smaller body can produce. It is large enough that those processes interlock into a self-sustaining system of hostility. It is large enough that its influence extends across the full breadth of the solar system, shaping the fates of worlds that orbit hundreds of millions of kilometers away. Giant implies scale. What Jupiter actually represents is dominance. Gravitational dominance over the solar system's architecture. Magnetic dominance over the largest volume of controlled space around any planet. Atmospheric dominance in the depth, energy, and persistence of its weather. Radiative dominance in the intensity and lethality of its trapped particle environment. The real shock is not that Jupiter has big storms, Every gas planet has storms. The real shock is not that Jupiter has a strong magnetic field. Several planets have magnetic fields. The real shock is that Jupiter combines all of these into a single planetary system, where each form of violence amplifies the others, where the output of every destructive process feeds back into the engine that created it, and where the scale of every individual hazard exceeds anything produced by any other planet by factors of tens, hundreds, or thousands. Jupiter is not the most violent planet in the solar system because of any single feature. It is the most violent planet because it is a machine. A planetary engine whose fuel is its own mass, whose product is hostility at every physical scale, and whose operating cycle began before life existed anywhere in the solar system and has not stopped since. In every photograph, Jupiter looks peaceful, a sphere of painted bands drifting through the outer solar system in silence. But every swirl of colour in those images is a system of atmospheric violence, powerful enough to shred any structure ever built by human hands. Every empty-looking gap between the planet and its moons is saturated with radiation energetic enough to kill in minutes. Every elegant orbital curve traced by a Galilean moon is a path through gravitational forces strong enough to melt rock inside a world. Jupiter is the most violent planet in the solar system, and the most disturbing part is not the violence itself. It is that the violence is the planet. There is no version of Jupiter without it. Strip away the storms, the radiation, the gravitational destruction, and there is nothing left. The violence is not what Jupiter does, it is what Jupiter is. And perhaps that is the most important lesson Jupiter offers. Not a lesson about one planet, but a lesson about the universe. We live in a cosmos where beauty and violence are not opposites. They are consequences of the same physics, separated only by the perspective of the observer. From 1 billion kilometers away, Jupiter is a marble of swirling color, serene and ancient and impossibly elegant against the black background of space. From the cloud tops, it is a crushing, dissolving, electrically explosive atmosphere with no bottom. From the radiation belts, it is a particle accelerator running at energies that rival anything human technology has constructed. From the orbit of Io, it is a gravitational torturer that has been melting a moon from the inside for longer than life has existed on Earth. Same planet, same physics, different distance. Humans evolved on a gentle world. A world with a solid surface, a breathable atmosphere, a magnetic field just strong enough to deflect solar radiation without trapping lethal particle populations, and a gravitational field too weak to tidally destroy anything in its orbit. We developed our intuitions about planets on this world, and those intuitions tell us that planets are places, destinations. Worlds you could, in principle, visit, explore, and perhaps one day inhabit. Jupiter dismantles that intuition completely. It is not a place, it is a process. A physical system whose defining characteristic is the conversion of mass into multiple simultaneous forms of violence operating across every scale from the molecular to the solar systemic. The ancient Romans named it after the king of their gods. They chose better than they knew. Jupiter does not merely rule the solar system by size, it rules by force. Gravitational force that sculpts the orbits of worlds hundreds of millions of kilometers away. Magnetic force that controls the largest structure any planet has ever produced. Atmospheric force that grinds and crushes with a depth and energy no other world can match. Tidal force that reshapes moons from the inside out. Radiative force that sterilizes the surfaces of worlds that might otherwise harbor the conditions for life. Every telescope that has ever studied Jupiter has discovered that the planet is more dangerous than previously believed. The Voyager missions revealed the radiation belts were more intense than anticipated. Galileo revealed the atmosphere was deeper and more complex than models predicted. Juno revealed that the weather layer extends 3,000 kilometers down, that lightning operates through exotic chemistry never observed on Earth, and that the magnetic field is lumpier and more dynamic than anyone expected. The James Webb Space Telescope discovered a jet stream at altitudes no one was looking at. Every new instrument finds a new layer of hostility that the previous generation of instruments was not sensitive enough to detect. The pattern has held for half a century. There is no reason to believe it will stop. Jupiter is the most violent planet in the solar system, not because of any single storm, any single radiation belt, any single gravitational interaction. But because it is a planetary engine that converts its own mass into hostility at every physical scale, through every available mechanism, without interruption and without any prospect of stopping, it has been doing this since before life existed on Earth. It will continue doing this long after our sun has consumed its fuel and faded into a white dwarf. The engine does not require maintenance. It does not require fuel from outside. It runs on itself. And it has never, in 4.5 billion years, paused for a single second. The clouds are beautiful from here. They always will be. But do not mistake the distance for safety. The violence is real. The violence is permanent. And the violence is the planet.